Hi everyone, this is Dr. Santosh. So I am doing a series of lectures, human genetics. This is the sixth video in the series and sixth video in the topic structure of DNA. So today in structure of DNA we are going to talk about major and minor. Okay. So first let me introduce you to this analogy of DNA structure. So you can see this is a helical strand. So you can imagine somewhat this DNA is like helical strand. Now here what you can see is the backbone of this stair, and then you can see this steps of this stairs. So these stairs is analogous to furin and pyrimidine bases of this DNA duplex. So you can see here this plate is very much parallel to the floor of the floor. So when you put the DNA this way straight, the bases will be somewhat parallel to the floor. Backbone is sugar and phosphate. It will be around. It is a perpendicular like this, like the rod backbone is. So you can imagine the structure of DNA. Let's go to the real structure of the DNA with the animation. Now here you can see the DNA helical structure. So in DNA helix, you can see the rotating DNA helix. It is rotated. Now you can see here this base pairs. This base pairs, they are somewhat horizontal to the floor. Okay. So and this backbone, the backbone is made up of the phosphate and sugar. They are somewhat straight. So this is what DNA looks like. When you see closely, this is parallel to the floor, and this structure sugar, it is placed at the right angle to the bases. So this is the structure of DNA. So you need to understand the structure of DNA to understand really well to understand the major and minor group. After you have seen the 3D structure of DNA like this in animation, now you can correlate the DNA with this. So this is the structure when you see DNA from in cross section, from top or bottom. So when you see DNA from the top and bottom, then you can find the DNA is linked here with the N-glycosidic. These bases, they are bound with the sugar with N-glycosidic bond here and N-glycosidic bond here. So when you see N-glycosidic, it is very important to note this N-glycosidic bond to understand major and minor group. So when you see this N-glycosidic bond in all the nucleotide, all the base pairs, nucleotide base pairs, so with base they don't divide this base equally into two halves. So you can see when you draw a line from this N-glycosidic bond here and here also, so you will find the one face of DNA. Okay, one face of DNA will have concavity and other face of DNA will be obtuse. This is one face will be acute and other face will be obtuse. So this obtuse face of DNA is major group and this is minor group. Let's see here with the example of folded paper. So you can see this is folded paper. This is folded paper. Okay. Now folded paper, when you N-glycosidic bond of the DNA will form this type of thing. As you can see here, it will divide the base plate into uneven half and will create a groove. One, if you make a straight ladder out of DNA generally is helical. So when you straighten that helical and make it a straight, so the bond will look like this. So this face, outer face here, you can see it will be a kind of obtuse. So it will have more space than inner face of the DNA. So inner face of DNA here you can see it is minor group and the outer face of DNA is major group. So major group is wider it is the actual width of major group is 22 angstrom and the width of minor group is 12 angstrom. So this is the main thing you need to understand about major group and minor group. So what will happen is, because the size is big, so what is the significance of this major group is this, because this size is big, so protein has alpha helical structure. Alpha helical structure size fits well with major group. The major group has 22 angstrom. The alpha helical size of alpha helix is also around this size. Okay, so this alpha helix will fit well in major group, and in minor group there are only few proteins that will bind, but most of the protein they will bind to this major group, that or other phase of the one phase of the DNA. And then so you can see if you closely look at this bases here, you can see this bases when they form hydrogen bonding, and this N-glycosidic bond is a very important determinant of major and minor group. And if you see in minor group, so you will find minor group has this N as hydrogen acceptor, and the minor group between this GC base pair, guanine cytosine base pair, you will find A is there, acceptor. A means acceptor of hydrogen bond, and D is donor of hydrogen bond A. And here also you will see ADA. So there is no, if you see GC and CG base pair, you will not find any difference here. In minor group, major and minor group of AT and TA also, if you see AHA, acceptor of hydrogen bond and donor of hydrogen bond, this is hydrophobic, this basically as for hydrophobic, and this A for acceptor of hydrogen bond. Same thing you will see. So there is no difference. But when you see in major group, you will see the sequence is changed. Here AD, except this is acceptor of hydrogen bond, D for donor of hydrogen bond, A for acceptor of hydrogen bond, M. So ADAM, Adam will be the sequence here, but when you see TA, the sequence will be MADA. So the sequence will be different for this base pair than to this base pair. Also for this GC base pairing, if you see AADH and DHD, so sequence when the cytosine comes first and one later, so sequence is altered. So this is the significance, this sequence, because this is the sequence is different. So this protein use this sequence, different sequence, to actually find a proper location. So this is called specific binding. Your transcription, many transcription factor, they have a particular type of transcription factor binding element in DNA. There is some region in DNA where in that particular region only that particular transcription factor will go. For example, steroid hormones receptor are transcription factors. When the steroid hormone binds with its receptor, that receptor will go and bind on its specific location that is guided by this sequence. That type of binding is called specific binding. There is something called non-specific binding. Okay, non-specific binding is the histone binding with the DNA. So actually, non-specific binding, it is helped more by the phosphate bond here, phosphodiester bond, and in the backbone. But specific bonding is guided by this major group, and obviously that backbone, negatively charged backbone, help this protein binding, but guidance for a specific binding is there in major group, because you know the AT, TA, GC and CA, they are different. So this protein, they will recognize a particular sequence in that element, in that DNA element, steroid binding, for example, a steroid binding element. This is how the DNA, the protein will localize a particular segment and increases the transcription of the gene. Okay, now let's have again look with the major group and minor group in 3D structure again. So see, we will see in 3D DNA, the one phase will always be one phase of this unfolded DNA will always be major group, other phase will be minor group. Let's see that this thing in 3D structure. Now let's see how this major and minor group is present here in the DNA. Okay, here in the DNA. So let's see that. So when we see major and minor groups here, let's first have a look at the major group. So as you know, the major group is present in one phase of DNA. When you unfold this DNA in a stair, you make a straight stair rather than this helical. If you make it straight, so what will happen is this one part of DNA, you have the one part of DNA, this here you have this helix, This is major helix. You will find major helix going all the way on one face. Going all the way on one face will be major helix. Okay, and minor helix here. This is the minor helix. It will go other face of the same DNA. You will find it is minor helix like this. So this will be minor. Let's see the major helix and minor helix in 3D space field model. You see major group here. So this is major group. You can see find major group. You can rotate. The major group will be one face. So this is major group. Okay. This is major group. Distance between this is major group, and the minor group is this. Now we have seen major group. Major group you can find major group all the way. Okay. One face of this double helical is major group. This is major group. This is the place where protein will bind. The most of the protein binds here. Now let's talk about the minor group now. The minor group is this group. Okay. This group is minor group. So when you rotate this helix, so you will see the protein can slide on this minor group if any protein binds. Generally protein binds on the major groups. So protein generally binds on the major group. So again I am showing the major group. You can see this. This is the major group here. This is the major group. Protein binds here, and protein can slide upon this on one face. On minor group, this is minor group. Other is minor group. You can see this is the minor group. So if some protein has to bind on minor group, but generally protein does not bind. Only few protein binds on minor group. All the protein they bind on major.